Welcome to this explainer. Today, we're totally decoding the chemistry of matter. We'll start right down at the basic particles and build up to the absolutely ingenious techniques scientists use to pull them apart. Whether you realize it or not, almost everything you touch, eat, and breathe every single day is completely governed by the principles we're going to explore right now. All right, here's our roadmap. We've got 5 stops today. First, the makeup of matter. Then, homogeneous versus heterogeneous mixtures, moving into the science of solutions, checking out suspensions and colloids, and finally, the art of separation.
Kicking things off with Section 1, the makeup of matter.
Take a second to look around you. Almost everything you see is a complex chemical mixture. So, unlike a pure substance, which is made of just one specific kind of particle, a mixture is a combination of 2 or more pure substances. But here's the catch. Every single ingredient stubbornly keeps its own unique chemical properties. Think about sand mixed into seawater, or even the ingredients in butter and cheese. They're mixed, sure, but they haven't lost their individual identities. Now, what's really fascinating about mixtures is that there's literally no strict recipe required. You can mix the constituents in any proportion. Toss a little salt and water, toss a lot, it's still a mixture. Plus, when you combine them, there's no massive explosion of energy absorbed or evolved. And because those individual parts keep their original properties, you can actually pull the whole thing apart later using purely physical processes. We'll definitely get into those techniques a bit later. Moving right along to Section 2, homogeneous versus heterogeneous mixtures. Since matter mixes in all sorts of wild ways, scientists split it into 2 really distinct categories. It's all about contrast here. On one hand, you have homogeneous mixtures, like a sugar solution or rainwater. These are perfectly uniform throughout. Everything is evenly distributed, and the components are completely indistinguishable. On the other hand, you have heterogeneous mixtures, like chalk powder and water or iron powder mixed with sulfur. These are totally non-uniform. You can easily spot the different distinct phases just by looking at them.
Let's dive deeper in Section 3, the science of solutions.
Let's zoom in on those perfectly uniform, homogeneous mixtures, which scientists formally call solutions. Every solution is basically a 2-part system. First, you've got the solute. That's the minority component, the stuff actually getting dissolved. Then you have the solvent, the majority component, the heavy lifter doing the dissolving. So if you're holding a simple glass of salt water, the salt is your solute and the water is your powerful solvent. Now, this brilliantly illustrates something that surprises a lot of people. Solutions are absolutely not just liquids. Check this out. The air you're breathing right now, that's a gas in gas solution, where nitrogen acts as the solvent for oxygen. A tincture of iodine, that's solid iodine dissolved in liquid alcohol. And get this, the brass in a trumpet or a doorknob is actually a solid in solid solution. It's an alloy where solid copper acts as the solvent for solid zinc. How cool is that? Okay, so let's talk about concentration. This is really just about how much solute is packed inside that solvent. An unsaturated solution, it's still hungry, it can dissolve more solute. A saturated solution, though, has hit its absolute limit for a given temperature. It literally cannot hold anymore. But here's the trick. Temperature heavily dictates solubility. If you heat up a liquid solvent, it can suddenly dissolve way more solid solute. That is exactly how pancake syrup becomes a super saturated solution, holding on to way more dissolved sugar than room temperature water ever could.
That brings us to Section 4, suspensions and colloids.
All right, we're stepping out of those perfectly clear solutions and into the wild, visible particle world of heterogeneous mixtures. It's essentially a battle of particle sizes. True solutions are clear because their particles are smaller than a single nanometer. But suspensions, they have massive particles, over 1,000 nanometers. Muddy water is a classic suspension. It's totally unstable. If you leave it alone, gravity drags all those large dirt particles right to the bottom. But then you have colloids, like milk. Colloids sit right in the middle, between 1 and 1,000 nanometers. Their particles are just small enough to remain permanently suspended and quite stable, so they won't settle out, and you absolutely cannot separate them with simple filter paper. Colloids are super fascinating. The particles inside a colloid don't just sit there. They bounce around constantly in a random zigzag pattern called Brownian motion. And because these particles are suspended everywhere, they create this really cool phenomenon known as the Tyndall effect. Basically, they scatter light so effectively that if you shine a strong beam of light through a colloid, the actual path of the beam lights up and becomes distinctly visible. It makes the mixture look translucent rather than transparent. And as you can see from these examples, Colloid chemistry is literally everywhere in your life. Fog? That's an aerosol, just a liquid dispersed in a gas. Shaving cream is a foam, which is gas trapped in a liquid. And that block of cheese sitting in your fridge? That's a gel, meaning it's actually a liquid dispersed perfectly inside a solid medium. Seriously, it's chemistry you can eat.
Okay, so we've seen how matter combines in all these diverse, incredible ways. But this raises a huge question. If things mix so perfectly, how in the world do we force them apart? How do we isolate the pure substances we actually need?
Let's find out in Section 5, the art of separation.
We're looking at the everyday mechanical and physical procedures scientists use to separate mixtures. First up, distillation. This is perfect for miscible liquids, liquids that mix together flawlessly. Distillation weaponizes their different boiling points. Say you have a mixture of acetone and water. You slowly heat the flask. Because acetone boils at a lower temperature, it vaporizes first. That vapor travels into a condenser, cools down, and turns back into a pure liquid distillate, leaving the higher boiling point water trapped behind in the original flask. It's an incredibly elegant process.
But wait, what if the liquids refuse to mix at all, like oil and water? We call those immiscible liquids. For this, scientists use a separating funnel, which is basically letting gravity do all the hard work. You literally just pour the mixture in and let it sit. The liquids stack up naturally based on their densities. Oil is lighter, so it floats to the top. Water is heavier, so it sinks right to the bottom. Then you just open a little valve, the stopcock, at the bottom, drain the heavy water out, and boom, you've completely isolated the oil.
Next is separation by sublimation. And guys, this is honestly like a chemical magic trick. Some solids, when you heat them up, totally skip the liquid phase and jump straight into being a vapor. So if you heat a mixture containing common salt and a sublimable solid like ammonium chloride, the ammonium chloride instantly vaporizes. Those vapors rise up, hit the cooler walls of an inverted funnel we place on top, and instantly freeze back into a pure solid. It completely escapes the salt left sitting in the dish below. Now, why does this all matter? Because these exact physical separation techniques are working constantly in the background of your life. Centrifugation, spinning mixtures really fast to force denser particles to the bottom, is exactly how dairies separate cream from milk, and how diagnostic labs test your blood. Chromatography, using different solubilities to isolate drugs from blood samples, and coagulation, using chemical clumpers like alum, is literally the process keeping your city's muddy drinking water beautifully clear. It's even the same basic process, using acid coagulants to separate milk proteins to make the cheese on your pizza. Which leaves us with one final, kind of mind-bending question. If nearly everything you interact with daily is actually a complex mixture, what other invisible chemical separation processes are happening around you right now? Thanks so much for joining me for this explainer. Next time you pour a glass of milk, take a deep breath of air, or walk through a heavy fog, just remember the incredibly cool microscopic physical rules holding all that matter together.